packet that says Understanding Forces, and it has a little cartoon of a table with a brick sitting on it. All right. So today what we're going to be working on, you've started bringing up the idea of forces a lot while you were talking about the rollerblader. You were talking about things like Jill was talking about a pushing foot and a gliding foot. And then a lot of people were talking about grip on the floor, which is another kind of force. And then I started to hear some people talking about that it matters how heavy people are. It matters how heavy the object is that's trying to move because of gravity. And that's another kind of force. So what I want to do today is to help you guys begin to understand how you measure forces and how we draw them in on a diagram. Okay, so I've given you some tools, and I want to go through a couple of activities together, and then I'll let you guys work with your table group, and I'll come around and talk to everybody. So during this part, when it's like me up in the front of class, I need you not to talk to your partner, but in a couple minutes, I'll switch it, and then I want you to talk to your partner.
Okay.
Okay? So let's go through the beginning. Who wants to read the directions? Start where it says number 1.
Hold it straight up and down to be sure that it's measured 0
Newtons, like Isaac Newton. That's cool. He has a unit named after him.
Newtons. If it does that, then you should adjust it by turning the white ball on the top.
Okay, so everybody grab a spring scale and hold it by the loop with the hook hanging down to the ground.
I told you.
Just hold it on the loop part. Make sure that you're on the side that says N on the top of the numbers. If it says G, you're looking on the wrong side.
Okay, good.
You gotta look at the Newton side.
What's a G for? My grams.
Grams. But we're interested in Newtons. Okay, so everybody, including Juan, should be holding it like this and looking at it. Okay, find where the top of the plunger is and see if it lines up with the 0.
Plunger?
So this, mine is yellow on the inside, yours is brown gel on the inside. And see if it lines up with the 0. If it does not, mine looks like it's hanging on 2, but that doesn't make any sense because there's nothing hanging.
Mine lines up with
So I want, when there's nothing hanging on here, I want it to say 0. But mine's not quite adjusted correctly, so I'm going to see this white bolt?
Yeah.
Turn it so that it makes the screw go up or down to adjust so that your plunger is at 0 when you're hanging it like that. Okay, so I'm going to adjust it to get it where it needs to be. Alright. So when it has 0 things on it, it should say 0 newtons. Okay, is everybody done with that step?
Yep.
So,
0 is still like that.
okay, so Hanad, stop playing. Alright, Shauna, can you read hint number 2?
Okay, when you pull something with the spring scale, you should pull it straight in the direction of motion. If you want something to move sideways, pull it straight, not diagonally.
Okay, so don't do this yet, but in a minute I'm going to have you hook your hook to the brick and pull the brick. But the advice is that you need to hold the spring scale even with the table. When you pull it, you have to pull it straight. If you pull it up at a diagonal, you're lifting, you're not really pulling.
Oh,
And
cool.
so your measurement would be incorrect.
So like this? So like this?
Yeah. So yes, if you want to slide something, you'll just pull it like that. Okay? If you want to lift something, then you'll lift it straight up and down.
Yeah.
Okay? Jill, do you have a question?
No.
Okay.
I can.
All right, and then can you read hint number 3, please?
Be careful with spring scales. Don't stretch them too far because you can break them easily.
Okay, so this is something to pay attention to. This is why I gave every group 3 different colors of spring scales. the 3 different colors are like 3 different strengths of the spring. Like my yellow one is really strong. It goes all the way up to 50 newtons. Look at your green one and your brown one and see what it goes up to.
5.
All right, so we're going to learn one thing before we start using the spring scales. There's a special way that physicists draw forces. Okay, and it's all physicists communicate with each other this way. So we're going to learn it so that we can communicate with each other about forces too. Okay, so drawing diagrams number 1, it says draw the object you're studying and any other important objects like the table or the floor. Number 2, you're going to draw forces as arrows pointing in the direction that the force is pulling. If a force is pushing in real life, like a hand pushing the brick, you would still draw it so that it looks as if the arrow is pulling. So even if I went up to this brick and pushed it, I would still draw the arrow as if I was pulling it. That's the only sort of tricky part that physicists do. They draw pushes that look like pulls. Okay? All right. So let's try the first one. I put in a diagram for you up at the top, but we're basically going to generate a similar diagram. So let's do the first one. It says place a brick on your table. Place a brick on your table. Everybody got the brick on their table? Okay, and this is the part where I'm going to have you start talking to your partner, your table people. Okay, here's what I want you to talk about. I want you to talk about what you think are the forces that are acting on the brick when it is at rest on the table. What do you, Helena, what do you think this at rest means?
Not moving.
Not moving? Okay. So when it's just sitting still on the table. Okay, so I want you to talk with your group about whether or not you believe there's any forces acting on that brick right now when it's just sitting there. And I want you to talk about what your evidence is. And then we're going to draw a diagram together. Okay? So you have 1 minute to talk to your partner. Go. All right. So, Jaden, what do you think? Are there any forces that are acting on that brick when it's just sitting there?
Gravity?
Okay, so gravity.
Can
Can you tell me more about the gravity?
It's pulling it down right now.
Okay.
And you can tell because it's heavy and it has weight.
Okay, so like when you lift it up, you can tell that it's pulling down against your hand. Okay. Any other forces that people are thinking about?
That's gravity.
Just gravity?
Which they took.
Okay, Amy is looking at the diagram normal force. What is that?
The table holding the brick up.
Okay, so you're saying like that not only is the brick being pulled down to the table is
stopped.
pushing up. Like it's being stopped by the table. Okay? So let's draw what this would look like. So you can draw in a table. And then draw a brick. Okay, and then we'll draw in the force that Jaden talked about, the force of gravity, which is also the weight of the brick. So the way we can use a little symbol for that is that we can do F with a little W. Okay, and then the force that Amy talked about is the force of the table, but remember this is where physicists are a little weird maybe. The table is pushing or like stopping the brick, but we represent it like a pull.
Oh.
And the symbol is F with a little N because that force is called the normal force.
Oh, so it's force and then N stands for moment. It's like exponents but letter. Yeah, exponents with letter.
Correct. Right now, you guys are just sort of taking my word for it that this normal force exists. Okay, so on the next page, we're going to do a little test to try to figure out, like, is there some way that we could prove that the weight really exists and that the normal force really exists? Okay, so the next page is sort of a little experiment. Okay, all right. Flip to the next page. Okay, this is the part where I'm going to start coming around and listening in on each group. There's some bullets and some directions for what you should do, and then I would like you to stop and do some writing and drawing if you need to, or I would like you to do writing and drawing. You can do as much drawing as you need to. And then there's some places where you can do some measuring with your spring scales. I would recommend using the yellow one. Okay, so let's try this together. You can talk with your group, and I'm going to come walk around. I would suggest having somebody read the bullets to your group.
About 22.
No, like that.
Okay.
So hold the brick using your spring scale to measure the weight of the brick. Remember this number. Now connect two spring scales pulling against each other. Hold them up and down and pull until you can make the top spring scale read the same as what it read when it was holding the brick.
Okay, so let's do holding the brick to find out how heavy the brick is. So just hold it up. Hook it on there and weigh it. So hold it by the loop and see how many newtons it is. Or you're going to have to use all your muscles.
Oh, that hurts. Hold on. Oh my God, that's
So now how many newtons is it?
23, 24.
Now connect
Let's see.
You can have one help
up
you.
and down until and pull
How many newtons is
so
it?
you can make top spring scale read the same.
Like 3.
3?
Wait, where? Oh, right there.
Do you need help?
Oh,
Making me laugh. Okay.
yellow one.
Do it. Yeah, 23.
Okay, so let's write that down as the force of the weight.
We need a yellow one.
23 newtons.
So you guys still have to share yellow ones, is that what you're saying?
We need another yellow one because it says now connect two spring scales pointing against each other. Hold them up and down and pull until you can make the top spring scale read the same as what.
So, tell me again what you're going to do on this second bullet.
Now connect two spring scales pulling against each other. So like this.
So let's do like this. I'll hold this one and you pull down on it with another one.
Like, do we put it right here?
Turn it upside down though.
Dun, dun, dun.
Okay, so now let's do it with the yellow one. Let's cooperate with this other group and use their yellow one.
Samson, you have muscles.
Okay, so now, but wait, we gotta pull straight up and down. Okay, so read it again, Clayton. What are we trying to do?
23 newtons.
We're trying to make the top one say 23 newtons?
Yep.
Okay,
And the bottom one.
so let's see. Make the top one say 23 newtons.
Pull, Samson, pull. No muscles. Like,
Okay, what does the bottom one say at the same time?
2019. Oh wait.
So keep the top one at 23 and read the bottom one. You're gonna have to move your other hand, Samson.
I always tell. Is it at 23?
Somebody read the.
Tell me if it's at 23.
Yeah, so you
is that 20? Yeah, 3.
Yeah, 23. Go there at 23.
Okay, so let's think about that. So to make this one be like the brick, you had to pull this one with 23. So you had to pull this one with 23 in order to make this one say 23. Okay? All right, let's think about that for a minute. Okay. Talk about the next bullets with your group.
People having to.
So what does it say, Clayton?
Are both people having to apply a pulling force in order to make the scales read the same amount of newtons for the brick applied?
I say
And then how could you create an argument to support this claim using evidence?
one person has
I think because since the brick is 23, and then when you was pulling on the brick with this one, it was 23, that one has to make 23 to substitute for the brick.
Okay.
Equal whenever you pull one. And that was my evidence.
Okay, so here's the claim. So Clayton, can you read the claim that you're going to try to argue about?
Even when a brick is just sitting at rest on a table, there's a force pulling down and another force pushing it up. And the forces are equal when the brick is just sitting on the table. Possible evidence.
Do you agree with that claim? That there's a force pulling it down and a force pushing it up that's equal right now?
Yeah, because it stands still. So like since it's at rest, nobody's touching it. There's a force that's keeping it down on the table, but there's also a force that's not making it go through the table, but just like stand right there.
Okay.
Right now, gravity is pushing because of the gravity table.
So that gravity is the one that's keeping it, pulling it down. And then what's, like, I like how you said that it's not breaking through the table. So what's the force that's keeping it from breaking through the table?
Weight. Wait, no.
So the weight's the same as the gravity, right?
Okay, and then the normal.
Yeah. But what's making the normal force right now?
The air.
So you're saying that if I put it over here, it would just hover in the air?
Something like not letting it fall down.
Yeah, what's not letting it fall down?
The table.
So it's the table that's doing the normal force, is what you're saying? What if I hold it like this? What's doing the normal force now? So like this muscle?
Yeah.
Okay, you try it. Try it like how I just did and then feel your muscle. Is it making a force?
Yeah.
I know.
When you're not even trying to.
So it's making a force right now? Okay. So do you feel like you have evidence that there is a normal force? And evidence that there is weight? Okay, so now you guys can argue, you can write your argument, like if somebody didn't believe this claim, how would you convince them that there's weight and a normal force? Okay?
Right what we just said.
Yeah, right, what your evidence would be. Okay? Did you guys hear that? Okay, so you know what you're going to write there? Some evidence for proving that there's a normal force and proving that there's weight.
We just came up with a
Hold up, wait.
Okay?
Hold them up and down. Is it like?
No, we did that already.
Oh, you probably need another yellow one
Yeah. See.
to make it reach what did
No,
you
we
get
got
for
it
weight?
21. We got it to 21.
No, but see, this one goes over like that.
Yeah, so let me give you another yellow one.
Okay.
That's how you need it because then you'll see how much this weighs.
A yellow one for just a second.
Because then they'll act like this instead of this. Actually.
Okay, so I'll do the up and down one, you pull it,
I'll tell you.
and make sure that Helena can see the newtons. So how much was its weight?
21.
Okay. So pull till this is 21, and then Helena read the bottom one.
Keep on going, right there. Right there.
What does the bottom one say?
20. Sure.
This
21
is
now.
21?
Yeah,
Okay.
that's still 21.
Okay, so when I'm pulling up with 21, you have to pull down with 21. Okay.
Now do it on the brick.
No, we already did the break.
Okay, so now let's figure out what that means.
Well, we were thinking that it's like force. Like if you don't if the bottom person doesn't pull down, then there's not going to be the force. Like if the bottom person just kept it there, then it's going to go up. But like you have to force it so like the weight. It's like the bottom person was
bottom
the brick,
person is the
and then
brick.
the other person was like carrying the brick.
Yeah.
Okay? Or like in the
actually-
case of the table, the top person was maybe like the table.
Yeah.
Yeah.
Okay. So you can write in your numbers over here in the little box.
Oh. I don't normal.
Yeah.
So for the W one, you do. For this one, we do 21 in, right?
Yeah, they both.
Yeah, but what's different about them?
That one's
It was
pulling
weight.
down.
One's going down and one's going up. So how would you signal that one is down and one is up?
W.
The down.
No, the down is
with the
double.
down one. With the arrow. The arrow.
So this is a vector. Does that help you? How would you show that it's up versus down?
You would do W and N.
W, but like the
What if I
arrow,
wanted weight to be the one that was...
pointing down.
Okay, so how could you show it mathematically? I give you a hint. Let's call FW the positive direction.
Negative. Negative is up and positive. No, negative is down.
No.
Negative is up, positive. No, positives. Positives.
But for right now, I'm saying let's call weight the positive direction.
So it's
So which one's the weight, the down or the up?
the down.
The weight, this is the weight, right? The like the down,
Yeah.
and we're gonna call that positive.
So it means the up
Is negative.
is negative.
So which
that
one's
means
the up?
the FW.
No.
No, this one.
Yes.
Yes, it's up, so that's negative.
Oh,
And then this one would just be 21.
this is negative
Correct.
21.
W.
This is
21
negative 21
N
N. This is
Oh.
positive 21 N.
You got it now?
Yeah.
Yeah.
I know it seems crazy, but that's how physicists would do it.
Oh.
So like that?
Correct.
Okay, so
Oh wait, but not W's. This is still considered N for newtons. Okay, so the claim is, Helena, can you read the claim?
The claim is even when a brick is just sitting at a rest on the table, there's force pulling it down and another force pushing it up. And these forces are equal when the brick is just sitting on the table.
Okay, so this is like you're having dinner at home tonight and you look at your brother and you go, Muse, I have something to prove to you. Look, when I sit this on the table, there's a force pushing down and a force pushing up and they're equal. And Muse goes, you're crazy. Like, how would you prove to him, from the evidence that you've collected so far today, how would you prove to him that it has weight
On the bottom.
and that there's a normal force?
Well, if I had this at home.
Yeah, if you had scales at home, yeah.
So I would show him that if we had two equal ones and one was pulling up and one was pulling down, this one can't be like 31 and this one be 20 because it wouldn't be equal.
Okay.
And then to make it equal, they would have to be the same, so you know that there's equal
Okay.
on both of them.
Wouldn't there like be like a force pushing down because of the weight of the object?
Except that we think of it as a pull instead of as a push. Like gravity is pulling it down.
Yeah.
So
Like there's nothing up here cramming it down. It's that there's weight. The gravity is pulling it down. We just think of it as a pull instead of a push.
but then like we have to do. Wait, are you saying about the same thing? Wait.
You said pushing it down. And I'm just saying that in physics we think of it as pulling it down. Like that the gravity is pulling it down, not pushing it down.
So we're asked to show how the gravity pulls it down.
Yeah, like how would you prove to somebody that something is pulling this down right now?
It's not gravity in the air.
Okay.
Yeah.
So like if I brought it over here,
It's just gonna go.
yeah, it would just pull down, right?
Yeah.
So then how would you prove that the table is doing something?
Oh. Hold on. It's holding it.
It's holding it?
It's holding it from going all the way down because it's gonna pull. Like if it feels in the air and the table wasn't there, then it's just gonna go down. But the table is holding it there because the gravity. If we move the table, the gravity's just gonna pull it down.
What if you had a plastic? Like if you instead of a table, like you would compare it with a table, and then like it would be equal. So
like something that's really thin?
plastic, yeah,
Is that
and
what
then
you're
you put
saying?
it there,
Yeah, and it would like
you know that there's
crash
force
through?
coming.
Yeah. Or like, you know, if I hold it like that, like I can feel that there's force happening. So here, Jill, you do it. Like hold it on your side of the table.
Sugar man.
Do you have enough muscles to
I
hold
don't.
21 newtons? So like there's
I don't
force
feel
in
it.
your muscle right now, right? You're having to do some force.
It's just what I feel.
Just bones.
There's bones. There's no muscle in there.
There's a little bit.
So that's the same, like your hand is doing the same thing that the table has to do,
Because if you
right?
remove your hand, it's just gonna.
Table doesn't have muscles.
So you would.
No, but it's strong. We would say that it's still a strong table.
So you would.
Compared to your like idea of a plastic table.
Yeah. So in order to support the claim, like, could we do that, like an example of like the table is keeping it from like
Crashing through.
yeah. So that's how you would support your claim.
Yeah.
How?
And you could write it as sentences. Yes, you can. You could write it as sentences or bullets.
Could we do it as like a picture?
Yeah.
like you know, like I don't know, can you see
Like a
that?
force diagram?
Yeah, and then there's like the table, point to the table is like keeping it from falling.
Yeah.
Okay. And then if like I was like, because I was thinking that I could do like a table with the brick, and then like I'm gonna do like the brick and then without the table. It would
Yeah.
just-
Yeah, go for it.
Okay.
Okay, so what's the number that you measured for its weight?
22.
22 newtons?
Yeah.
Okay, so you can write that in, 22 newtons.
Well, I should write
Just put N, capital N. Okay, and then let's make an inference. If the brick is like being pulled down with 22 newtons onto the table, how hard do you think the table is pushing up?
22.
Okay, but it's in opposite direction. So how would you show that it's the opposite direction? Yep. Got it.
Okay, we gotta.
Which seems kind of crazy.
It's like the grids.
Yeah.
Grids go up and
Yeah.
down like that.
Yeah, like the axis, yeah. And it seems crazy to have like negative amount of force, but remember it doesn't mean like less than 0, it means direction.
Oh.
Okay, and then what are you guys thinking for some evidence that you could use, like if you went home and told your mom that you learned today that this brick is being pulled down and pushed up equally, and she said, you're crazy. How would you prove to her that it's being pulled down and pushed up
Because like
equally?
gravity's pulling it down, and like the table is like keeping it up because like it's like not just falling down and stuff, like so it's like just staying on the
Okay,
table.
so you're saying like if you held the brick over here where there's no table and let go,
It would just fall.
it would just fall down. Okay, so that you're saying that that's evidence for gravity and evidence that the table is doing something? Okay, what if she said like, no, it's still, the table's not really pushing? Can you think of another way that you could prove that the table is pushing?
Okay, you guys, stop moving around. You're working here. What's gonna work?
Hold your hand like this next to the table. Are you having to use any forces?
Yeah.
Yeah. How much force do you think you're using right now? I mean, if this is 22 newtons, how much force do you think your muscle is having to do right now?
22.
Negative 22, right? To be able to hold it up. And you're having to work kind of hard to be able to hold it up. So the table must be having to work hard too,
Oh yeah.
right?
That is like programmed.
Yeah. Yep. Does that make sense? As evidence for the normal force?
Oh, I'm gonna sell tables and I'm gonna say robots.
Okay, so you can, looks like you're starting as sentences. You could do sentences, you could do bullets, you could do bullets and a picture, you know, anything like that. Okay, sentences is fine. Okay, yeah. So you measured, your weight was 22. 22, what's the unit?
Plus.
N, okay? And you're saying that the weight is positive 22? Is the normal force going in the same direction as the weight?
No, it's negative.
So you're going to call that one negative, okay? Which seems crazy because it seems like it's less than 0, but that's not really what it means. It just means different direction, okay? All right, and then the next thing to think about is what if you went home and at dinner tonight when you're sitting around with your family, you're trying to tell them that you learned this thing in physics today, and they tell you that it's crazy that there's a force pulling down and a force pushing up that's equal. How would you convince them? What evidence could you use to prove that there's a force pulling down and a force pushing up?
Well, if you let go of the brick, it dropped to the ground. So that means there's a force pushing it down.
Okay,
And
pulling it down.
yeah, pulling it down. And when it stops, that means there's a force kind of stopping it
Okay.
too. So
Okay. So what if they say like, okay, I agree with you that there's a force pulling it down, but I still don't think the table is doing anything. What's another piece of evidence that you could use to prove that the table is doing something?
The table, like for example, like if you push the thing off the table, then it will keep on falling. But then, like they put it on the table and then they stopped falling.
Okay. Bradley, put your hand like this, even with the table.
Can I go to the bathroom?
Yes. Are you having to do any forces over here?
Yes.
How much force do you think you're having to do? How much? If this is 22 newtons,
I don't know. It's just.
how much force do you think, what's your normal force of your arm right now? If this is, what do you think? If this is 22 newtons, your arm is having to do 22 newtons of force, right? So you're having to work pretty hard to be equal to the table. Okay, Amy wants to try it.
It's not that hard.
So there's your 22 newtons of muscles.
It's not that hard.
So does your arm, do you now have like evidence in your arm for the normal force? Okay. So do you understand the question?
Yeah.
What if the table wasn't made out of table? What if it was made like out of
table.
Yeah, well, I don't know. Oh, these are wooden, I guess. What if it was made out of tissue paper? You know, like
it would just
like
fall
Kleenex.
through. Yeah.
Okay, and then follow it all the way through. Like, why would it fall through?
Because the tissue paper is not heavy enough to hold the brick, and since it's not equal, like both 22 positive and negative, like since it's that weak and the brick is that much heavier, it will just go through.
So if we had a tissue paper table, which force are we missing?
The normal force.
Yeah, so the normal force is way too small
Yeah.
for the amount of weight.
So it doesn't balance it out.
Right.
This one does.
Yeah. Okay, good. So how many newtons is it taking you to be able to pull it? 5. So keep pulling at a speed. So 5, you're saying it takes 5 newtons to pull it? Okay. Okay, so your pulling force is 5 newtons. What's its weight?
21.
Okay. What's its normal force? What's the normal force from the table?
21.
Positive or negative?
Negative. No, wait.
Positive. Right? Because pulling up is positive.
Right here, it was positive.
So if we choose positive to be the weight, then normal force has to be negative.
Negative.
Okay, then it'd be negative. Yeah, this is F.
Did you, when you were pulling it, did it feel like anything was kind of pulling against you?
Yeah. But isn't
What?
like the weight of it, like
What else?
the friction?
What if it was on ice?
That question again.
Like what if this was really slippery?
Oh.
Do you think it would?
It'd be way more better because it just slide on it.
Okay, how come? You just said it, friction. So you weren't wrong to have that arrow there.
This is
We just-
pulling. Didn't know
It's
why.
just hard to know how much it is.
Yeah. So just like, okay.
But
so.
you weren't wrong because it does grab the table a little bit, right? Why?
Because it's pushing against. It's going this way, not that way.
So you're saying like because we called the pull positive, then the
Because like,
friction
for
would be
example,
opposite.
this is like where 0 is, and then it's like going that way, just trying to keep it that way, and this is the positive line. So then
It's like a number line.
Okay.
Like if you start at 0 and then you go backwards, it's pulling
Yeah,
that direction.
I like that
then it's
idea.
gonna go negative. So it'll be negative.
This with
say like
5,
the
how much
brick
did
is
it
pushing
weigh?
down on
5
the
newtons to
table,
pull it? So if I'm pulling with 5 newtons,
How hard
positive
does the
5
table have
newtons,
to
you're
push
saying
up
that
to carry the brick?
the friction that this has is
same?
also positive?
Positive or negative?
So it's helping me pull?
You sure? So they both like
Oh,
push
no.
down?
Oh, negative.
Okay, so it's not helping me pull.
Negative.
How come?
Because it's not helping me pull.
So you're saying like it's the friction is actually like grabbing it that way. Like it's the opposite of my pulling.
Force normal. Would it have to be pushing the same as that?
Would
the
it?
other way? But the other way?
What do you think?
Yes.
Why?
Because that's how much it would have to push to hold it up. Because if it had less, then it would break through the table. And if it had more, then you could put more weight and stuff.
If you had more, it would like push the brick up.
Oh,
Like it would kick it up off the table.
I That's weird.
It'll be
So it
floating.
would have to be the same.
But I like what you said, the same but opposite. How would you show the same but opposite? Yep, and remember that it is newtons, not grams. There you go.
Don't measure in
Okay.
grams.
And then this is asking, we don't know what the force of friction is yet, but do you think that it would be positive or negative?
Negative.
How come? Like if I'm pulling with +5, why would you say that the friction is
Because
negative?
it's rubbing against the table, and that's what's making it not go as easily. It's like stopping it.
Okay, so
But you're pulling harder.
So it's
than-
like the friction is like tug of war against me.
but you're pulling a lot harder.
I'm overcoming the friction. Yeah. Okay. So just put some of those ideas down in that box, and then you're ready to go on to number 3.
These feel the same.
Okay.
No, let's pull out 14 because it's Valentine's Day and 14 is a lucky number today.
No, it's not.
No, I just want to pull out to Valentine's Day.
14 is my unlucky number.
Okay, let's go to 14. Ready, set, go.
You passed 14 a long time ago.
Okay, I'm at 14.
How much are you at? What's it doing?
Nothing.
Okay.
Because it's equal.
Because it's
Okay,
equal
so
force.
now just draw it, write about it,
So,
and write down your data.
wait, is this supposed to be like this?
Yeah.
And it was being pulled both ways.
It's like doing 14 positive minus negative 14.
And you stay at 0. Exactly. And it's being pulled both ways.
So it's not